this video, we're going to learn about antiderivatives and how they relate to differentiation. We'll start with the definition of an antiderivative and see how antidifferentiation works as the reverse of differentiation. Then we'll review a table of common antiderivatives and work through lots of examples so you'll know exactly how to approach these types of problems. Be sure to download the free guided notes to follow along and work through the examples with me. Let's start by learning how to find an antiderivative. If we're given a function capital F of x is equal to x squared, we can let little f of x be its derivative, and that's equal to 2x. Little f of x is the derivative of capital F of x, and then capital F of x is called the antiderivative of little f of x. An antiderivative of a continuous function little f of x is a differentiable function capital F of x whose derivative is equal to the original function little f of x. This process of finding an antiderivative is called antidifferentiation, or it's called integration. Antidifferentiation is just the reverse operation of differentiation. Let's walk through an example to see how this works. We are given little f of x is equal to 1, and we want to find capital F of x. Let's start by writing down little f of x is equal to 1, and then capital F of x is the antiderivative of little f of x, and we want to think of this as the function whose derivative is equal to 1. If we take the derivative of x, we get 1, so capital F of x can equal x. If we let capital F of x be equal to x plus 1, does its derivative still equal 1? It does. What about capital F of x is equal to x minus 1? That derivative is also equal to 1. Let's go over here to the right and let's graph these solutions. This is the graph of x plus 1. And then this is the graph of x. And this is the graph of x minus 1. There are actually an infinite number of antiderivatives. And they all differ by a constant. Instead of specifying the constant, we can say that capital F of x is equal to x plus c, where c is a constant that ranges between minus infinity and infinity. Capital F of x without a constant or with a particular constant is called an antiderivative of little f of x. And then capital F of x plus c is called the most general antiderivative of little f of x. Let's now look at some common antiderivatives that you're going to need to know. I've listed the function on the left and the antiderivative on the right. The antiderivative of a constant a is equal to ax plus c. Whenever you write an antiderivative, you always want to include that plus c. The antiderivative of x to the n, as long as n is not equal to -1, is x to the n plus 1 all divided by n plus 1 plus c. On the right, I have taken the derivative of this function, x to the n plus 1 divided by n plus 1 plus c, just so that you can see how it all works and then it's equal to x to the n. I always like to show students that because I feel like that formula is not intuitive, without thinking about it in terms of differentiation. The antiderivative of x to the minus 1, or 1 over x, is equal to the natural log of the absolute value of x plus c. That's one that you're just going to have to memorize. Now let's look at some exponential functions. The antiderivative of e to the x is e to the x plus c. That one makes sense because the derivative of e to the x is e to the x. And then the antiderivative of b to the x is b to the x plus c divided by ln b. Next, I've written down the antiderivatives of some trigonometric functions. Let's look at the antiderivative of cosine x. That antiderivative is sine x plus c because the derivative of sine is cosine. Likewise, the antiderivative of sine x is minus cosine x plus c because the derivative of cosine is minus sine. So you need another minus sign to make it positive. Just remember that when you're taking the antiderivative, the signs are opposite from when you're taking the derivative of sine and cosine. Next, we have the antiderivative of secant squared x. That is tangent x plus c. And then the last trig one that I have is secant x tangent x, and the antiderivative of that is secant x plus c. The next two that I've written down have antiderivatives that are inverse trig functions. This is the first one. That antiderivative is inverse sine x. And then our second one, 1 over 1 plus x squared, that antiderivative is inverse tan x plus c. And then for completeness, I put down two hyperbolic functions, cosh and sinh, and their antiderivatives are sinh x and cosh x plus c. I think antiderivatives are hard the first time you see them. One good way to remember when you're starting out is to just think, what function do I take the derivative of to get this function? For instance, when you're finding the antiderivative of cosine x, you want to think, what function do I take the derivative of to get cosine x? And that function is sine x. And then you have to remember to add a plus c onto it. We're going to walk through 5 very common general antiderivative examples, and I'll show you everything you have to think about when you're doing these types of problems. In these examples, we are going to find the most general antiderivative of the function. That means that we're going to have to include a plus c with our answer. The first example that we're going to look at is f of x is equal to 4 plus x squared minus 5x cubed. Just to make things easier, over here on the right, I've written down the function x to the n, as long as n is not equal to minus 1, and its antiderivative x to the n plus 1 divided by n plus 1 plus c. In this first example, I want to begin by rewriting our function little f of x as 4x to the 0 plus x squared minus 5x cubed. That x to the 0 is going to help us learn how to find the antiderivative. If you're finding the antiderivative of a little function f of x, then that antiderivative is typically notated as capital F of x. So we're going to say capital F of x is equal to 4 x to the 0, and then we're going to add 1 to our exponent and divide by that exponent. Now let's do the same thing to the next term. This is x to the 2 plus 1, all divided by 2 plus 1, and then we have minus 5x to the 3 plus 1, all divided by 3 plus 1, and then we have to add a plus c. This gives us capital F of x is equal to 4x plus 1/3 x cubed minus 5 over 4 x to the 4th plus c. And that's our final answer. In our second example, we're given the function little f of x is the fourth root of x cubed plus the third root of x to the fifth. I chose this one because I want to show you that before you find the antiderivative, it's best to rewrite the function. So we're going to rewrite f of x as x to the 3/4 plus x to the 5/3. Now we can find the antiderivative much easier. Our antiderivative is capital F of x, and then it's going to be x to the 3/4, and we're going to add 1, and then we're going to divide by that exponent, 3/4 plus 1. And then we're going to do the same thing to our second term. This is x to the 5/3 plus 1, all divided by 5/3 plus 1 plus c. Let's go ahead and simplify this. 3/4 plus 1 is 7/4, so this is x to the 7/4, all divided by 7/4. And then our next term is 5/3 plus 1, so that is 8/3. And then we divide by 8/3, and we have our plus c. And then we're going to write our final answer in a little bit easier form. We're going to take the 1/7/4 and we're going to write it as 4/7 x to the 7/4 plus 3/8 x to the 8/3 plus c. And there's our answer. In our third example, we're given a function little f of x is equal to 5 minus 4x cubed plus 2x to the 6th, all divided by x to the 6th. Because we have one term in the denominator, we can break up our function into 3 separate pieces and then write each piece as x to a power. Doing this, we can write f of x as 5 over x to the 6th minus 4x cubed over x to the 6th plus 2x to the 6th over x to the 6th. You can only do this when you have one term in the denominator. We now need to rewrite this so that each term is x raised to a power. This is f of x is equal to 5x to the minus 6 minus 4x to the minus 3 plus 2. Now we can go ahead and take the antiderivative. Our antiderivative, capital F of x, is equal to 5x. Now we're going to add 1 to the exponent, and we get minus 6 plus 1, all divided by minus 6 plus 1, minus 4x to the minus 3 plus 1, and we divide that by minus 3 plus 1, and then we have a constant 2, and we're going to multiply that by x, and then we add on our constant c. Let's now simplify this. This is capital F of x is equal to 5x to the minus 5, all divided by minus 5, minus 4x to the minus 2, all divided by minus 2, plus 2x plus c. Now we just have to simplify it once more, and we'll get our answer. Capital F of x is equal to minus 1, all divided by x to the 5th, plus 2, all divided by x squared, plus 2x plus c. And there's our final answer. Our last two examples are different than our first three because they involve exponential and trigonometric functions. In example 4, we're given the function little f of x is equal to 5e to the x plus 2 divided by x. We don't have to simplify this function at all. We can just go straight ahead and take the antiderivative. capital F of x is equal to 5. The antiderivative of e to the x is just e to the x. So we have 5e to the x plus 2 times 1 over x, and the antiderivative of 1 over x is the natural log of the absolute value of x, and then we add on our plus c. And there's our answer. In our fifth example, we're given a function little f of x is equal to 2 sine x minus secant squared x. We also don't have to simplify this one before taking the antiderivative, and we can just go ahead and take it. Capital F of x is 2 times the antiderivative of sine x. The antiderivative of sine x is minus cosine x. And then we subtract off the antiderivative of secant squared, and that is tangent x. And then we add a plus c. We can rewrite this as capital F of x is minus 2 cosine x minus tangent x plus c. We're now going to walk through 3 antiderivative examples where we're given a second or a third derivative and we want to find the original function. In all 3 of these examples, we're going to find the function little f of x. In our first example, we're given that the second derivative of little f of x is equal to 2 plus x cubed plus x to the 6th. We are first going to need to find f prime of x because f prime of x is the antiderivative of f double prime of x. And then we can find f of x because that's the antiderivative of f prime of x. Our first antiderivative is f prime of x, and that's the antiderivative of f double prime, and we can write that down. The antiderivative of 2 is 2x, and then the antiderivative of x cubed, we're going to add 1 to our exponent, so this becomes x to the 4, and then we divide by whatever we get in that exponent. And then our next function, we have a 6 in the exponent. So for this, we're going to have x to the 6 plus 1, which is 7, divided by 7. And then we can't forget to add on our constant c. Now we can find f of x. It is the antiderivative of f prime. And we're going to get 2. And then think of the exponent of x being equal to 1. So we're going to add 1 to that. So this becomes x squared over 2. And then we get an x. We had a 4. Now we're going to get a 5. So x to the 5th over 4 times 5. And then our next exponent is a 7. So we get plus x to the 8 divided by 7 times 8 plus c. That gets an x added onto it because the antiderivative of a constant is a constant times x. And then we have to add on another constant, and we're going to call that d. Now all we have to do is just simplify our answer. F of x is equal to x squared, our 2's cancel, plus x to the 5th over 20, plus x to the 8th all over 56, plus cx plus d. And there's our answer. In our next example, we are given that f double prime of x is 20x cubed plus 12x squared plus 4, and we're also given that f of 0 is equal to 8 and f of 1 is equal to 5. This type of example is called a boundary value problem because we're given the values of the function at 0 and at 1. I'm going to write a diagram just to make this a little bit more clear. We'll label this as x, and then we'll put down x is 0 and x is 1. And at 0, we have our function equal to 8, and at 1, it's equal to 5. And that's why it's called a boundary value problem, because we're given the function value at our boundary points 0 and 1. Let's start by finding f prime of x. F prime is the antiderivative of f double prime, and this gives us 20. We have an x cubed, and we're going to add 1 to that, so this becomes x to the 4 over 4. And then we have 12. We now have an x squared, and we're going to add 1, so this becomes x cubed over 3. And then whenever we have a constant, we have to tack on an x, and then we also have to add a plus c. Before we go on to find f of x, let's go ahead and let's simplify this. F prime of x is equal to 20 divided by 4, which is 5. 5x to the 4th plus 4x cubed plus 4x plus c. You always want to simplify before you take an antiderivative again. Now let's go ahead and find f of x. It's the antiderivative of f prime of x. And this is going to be 5x to the 5. We're just adding 1 to 4 divided by 5 plus 4x to the 3 plus 1, which is 4, divided by 4, plus 4x, think about that as a 1. We're going to add 1 to that, so 1 plus 1 is 2, so we have an x squared over 2. And now we're going to have a cx plus an additional constant because we took another antiderivative, and we're going to call that d. Now let's go ahead and simplify again. F of x is equal to x to the 5th plus x to the 4th plus 2x squared plus cx plus d. Notice that in this answer, we have two constants, c and d. We can eliminate those two constants using our two boundary conditions. F of 0 is equal to 8 and f of 1 is equal to 5. The first thing that we're going to do is to let x be equal to 0. So we have f of 0. That is just equal to d, so that's really nice. And that's going to be equal to 8 because we were given that f of 0 is 8. Now let's find f at 1. All we do is go back right up into this equation. Let me go ahead and let's highlight this. And we're going to substitute x as 1. So this gives us 1 plus 1 plus 2 plus c plus d. And that, looking back up to our original problem, is equal to 5. This gives us 2 plus 2, so this is 4, plus c plus d. We know that d is 8, so let's put that in, is equal to 5. So we have c plus 12 is equal to 5, and that gives us that c is equal to minus 7. Let's highlight here that d is 8 and c is minus 7 because we now have to substitute those back in to our function. Our answer is f of x is equal to x to the 5th plus x to the 4th plus 2x squared minus 7x plus 8. And that's our answer. One nice way to check this answer is to let f be equal to 0 and then 1 and make sure that you get 8 and 5. And then you can check it even further by taking two derivatives, and you can see that you get 20x cubed plus 12x squared plus 4. In our third example, we are given that f triple prime of t is equal to sine t, and we're also given that f of 0 is 1, f prime of 0 is 1, and then f double prime of 0 is also 1. This is an example of an initial value problem because we're given the value of the function and its derivatives at time t is equal to 0. Let's start by writing down our function. F triple prime of t is equal to sine of t. To find f of t, we first have to find f double prime of t and then f prime of t, and then we can find f of t. So let's find f double prime of t first. That is the antiderivative of sine t. The antiderivative of sine t is minus cosine t. And we add on a plus c. Now let's find f prime of t. It's going to be equal to minus the antiderivative of cosine t. That is sine t. And then with our c, we have to multiply it by t. And then we have to add another constant because we just did another antiderivative. And we're going to call that constant d. F of t is equal to minus the antiderivative of sine t. That is minus cosine t. We did that earlier. Plus c. And then the antiderivative of t, we're going to add 1 to the exponent. Think of that as a 1. And then divide by that number. So that's dividing by 2. And then we have a d times t. And we have to add one more constant, and that is e. One thing to keep in mind is if you are given a third derivative, when you find your original function, you are going to have 3 constants. The number of constants that you get is equal to the number of derivatives that you start out with. Now let's go ahead and let's simplify this. We have f of t is equal to cosine t plus 1/2 c t squared plus dt plus e. Now what we want to do is we want to find c, d, and e. And to do that, we are going to use the 3 conditions that were given up here in our original problem. Let's start with f double prime at 0. Let me go up and highlight this so you can see where we are looking. We are looking right here. If we let t be equal to 0, we get minus cosine 0 plus c. Cosine of 0 is 1, so this is minus 1 plus c, and we set it equal to 1 because that's what we were given in our original problem. And this tells us that c is equal to 2. Now let's look at f prime at 0. Let's go ahead and highlight that now. That is right here. So we're going to let t be equal to 0. This gives us minus sine of 0 plus c times 0 plus d. Sine of 0 is 0, so this is just d, and it is equal to 1 because that's what we were given originally. Now let's look at f at 0. That is right here. We're going to let t be equal to 0, so this is cosine 0 plus 1/2 c times 0 plus d times 0 plus e. Cosine of 0 is 1, so this is 1 plus e, and this is equal to 1. Again, back up in the original problem, we were told that f of 0 is 1. So this tells us that e is equal to 0. Now that we know c, d, and e, we can write down our answer. F at t is equal to cosine t plus 1/2 times c, which is 2, t squared, plus d, which is 1, times t, plus e, which is 0. So our final answer looks like this. It's cosine t plus t squared plus t. The biggest mistake I see students make when doing this type of problem is forgetting to add on a constant every time you find an antiderivative. So just make sure to do that. In this application example, we are given an acceleration function and we want to find the corresponding position function. We are told that a particle is moving with the given data, and we want to find the position s of t of the particle. The data that we're given is that the acceleration at time t is 12 sine t plus 3 cosine t. And then the position at 0 is 0, and the position at 2 pi is 10. To find the position function, we first need to find the velocity function, because the velocity is the antiderivative or the integral of the acceleration. And then we can find the position function s of t, because it's the antiderivative or integral of our velocity function. Let's start by writing down our acceleration function. A of t is equal to 12 sine t plus 3 cosine t. And now we can find our velocity. It is the antiderivative of the acceleration, so that's 12. And the antiderivative of sine t is minus cosine t plus 3 times the antiderivative of cosine, and that's equal to sine t. And then we can't forget to add on a constant. Whenever you take an antiderivative or an indefinite integral, you have to add on that constant. Let's go ahead and let's rewrite this before we take another antiderivative. This is minus 12 cosine t plus 3 sine t plus c. Now we can find our position function. It is the antiderivative or integral of the velocity. This gives us minus 12. The antiderivative of cosine t is sine t plus 3 times the antiderivative of sine t, which is minus cosine t. And then with our constant, we multiply that by t, and then we have to add on a second constant, which we're going to call d. Instead of c and d, you could also use c1 and c2. Now what we need to do is find what c is equal to and what d is equal to. And to do that, we are going to use that we were given originally back up top here, that s of 0 is 0 and s at 2 pi is 10. Let's first let t be equal to 0. So s at 0 is going to be minus 12 times sine 0 minus 3 times cosine 0 plus c times 0 plus d. Now let's see what this is equal to. Sine of 0 is 0. Cosine 0 is 1. So this is just minus 3 plus d. And that is equal to 0, what we were given originally. So this tells us that d is equal to 3. And let's highlight that so we won't forget it. And now let's find s at 2 pi. S at 2 pi. Let me highlight that we're going back up to that line to find s at 2 pi. It is equal to minus 12 times sine of 2 pi minus 3 times cosine 2 pi plus c times 2 pi plus d, and we can go ahead and add in that d is 3, so that gives us a plus 3. Now let's see what this is equal to. Sine of 2 pi is 0. Cosine of 2 pi is 1. So this is minus 3 plus 2 pi c plus 3. And that is equal to 10. The minus 3 and the 3 cancel. So we get that c is equal to 10 divided by 2 pi, which is just 5 over pi. And we'll highlight that. Now, all we have to do is just substitute in c and d into this equation right here. This gives us s at t, that's our position function, is minus 12 sine t minus 3 cosine t plus 5 over pi times t plus d, which is 3. And there's our final answer. Remember, with these types of problems, you can always check your answer by taking two derivatives of the position function, That will give you the acceleration, and that will tell you if your answer is correct. And that's it. You've learned the definition of an antiderivative, reviewed a table of common antiderivative formulas, and practiced finding general and specific antiderivatives. To really understand these concepts, make sure to work through plenty of practice problems on your own.
If this video has been helpful to you, please consider subscribing to my channel. Keep believing in yourself and have a great rest of your day.